Okay, the meeting has just started being recorded. Please just confirm with me. Are you able to see my screen and hear me very well? Please give me a thumbs up if the screen is visible and my audio being clear as well. Thank you. Right, so section B was about briefly a brief explanation, and each question carries 8 marks. So basically 8 by 5. um, I think if you do that calculation, it can give you something like 40. Right. So section A 40, section B 40, section C just should be 20 marks. So let's see, section A was how many marks? Okay, so 4 by 5, that's 20. So section A 20, section B 40, and section C 40. Right, so we begin. Briefly, answer all questions in this section. Each section carries 8 marks. So the question number B1, using diagrams, illustrate how each push and pop operations are carried out on a stack. Explain leaf-4 concept. Okay. Okay. So let us do this. So let us do this. Okay, so this is basically what the question demands, and okay, and the question is using diagrams illustrate. So using diagrams, not diagram, illustrate how push and pop operations are carried out on a stack, and you're required to explain what last in first out is. So first thing first, you create a stack. Okay, so stack, basically take note, this is the capital letter. Okay, just like your programming. So this is a stack, then you give it a stack name, you create a new stack. Okay, then you put in size of a stack there. Okay, so I'm not really sure if you remember this concept from programming point of view. Let me ask, do you remember that concept from programming point of view? Do you remember that concept from programming point of view? Previous does remember. Okay, anyone else that do remember? If you don't remember, please give me a thumbs down. If you do remember, a thumbs up. If you don't remember, please give us a thumbs up. Please pardon me for that. English is not my first tongue. If you don't remember, give us a thumbs down. If you do remember, a thumbs up. Please be responsive so that we make the progress. Okay, for those of us who do remember, before I just come in, what does this signify? Please unmute yourself. What does that mean? When it comes to programming, there are terms that we give to this here and this here, and this is exactly as that. There are names given to this. Yes, this is created using a new keyword. Okay, this is an object. Yes, this is an object. Then new is used to create what? This? No, not an array. Not an array. You guys have forgotten your programming. Huh? Okay, what is it exactly? Okay, this is an object. This is a keyword used to create what? This is the same as this. That is one of the characteristics. I'm trying to open up your minds. Anyone else? Anyone else? Okay, let me give you a definition. Dash is a special method. Dash is a special method. Dash is a special method. That's a clue. Hmm? Exactly. So that's a constructor. That's what. Then what's this? Then what's this? Then what's this? Okay. Anyway, we are not learning programming. Just the thought of. Please pardon me for that. Yeah. I was doing something for my grandfather. Let's concentrate now. So you create a stack like that. Okay. So always remember. Okay. That's a class name. Okay. So this is a class. A constructor is always the same as the class. So you create what we are calling a stack. Then you create the object for that. Then a new keyword. Then the constructor, the size, you pass in the size there. Then you begin the concept of push and pop using the object. So when you say s dot, then push, you are saying first thing first, please be very specific. So when you say 1 stack is equals stack s, you can put x here, doesn't matter. Stack is equals to new stack, then the size there. What you are creating is an empty container. Okay, it's more like you just bought a bag from wherever you're buying it, be it in Kamwala, be it in shops, and so on and so forth. What you are creating is an empty bag, okay, where you are going to now be stacking those objects. Okay, so stack is equals to new stack, then the size there. Basically, you have to show 1 1. These have to match. Okay, you have that. Then 2, you now begin putting objects in there. Right. So first thing first, you use this object, then say dot push. Okay, you get the same object. Okay, because this is the object you created. You get the same object, then put a comma there. What we are saying, you have a string of an object that you have to push to this stack. Okay, so we are pushing this A to S. So this is basically S. So you put it there, and that has to match that. Please, there was a moment I made this mistake. I think especially on a test, the lack of labeling, and they denied me marks. Very convincing. And I agreed to that. You shouldn't make the same mistake, most especially where the exam is concerned. Then s dot push have at least 2 pushes, at least 2. S dot push, then you get the same s, which is this guy. Pass it there. Then you are saying you want to push this B on top of this stack. So the next time you're gonna have a container of A, then you put in your B. S dot push, we want to push C there. Okay, then you want to pop out s dot pop, then you say s comma, that means we want to pop c from this guy. Again, you don't pop out what is not there. Remember, it's the last in, first out principle. That's what a stack is. Because if you are putting clothes, you put clothes one on top of the other. So you can't go to a cloth number 3 minus touching the last cloth that you put in there. That's quite important. So the first guy that you are going to pop out is the last guy that you put in there, and that's 4. You label. So when you pop out, you're gonna remain with A and B. Then you pop B because that's what it is. You have that. If you want, you can also pop A so that you get back to an empty stack. You can also push in another, and so on and so forth. This is what they meant by using diagrams. But you don't just use diagrams, you need to be explaining what you are doing on the other side. That's when you earn full marks. Then the other part was explaining LIFO, so last in first out principle. Okay, so the last element in is the first element out. I hope that's clear. Kindly give me a thumbs up. I hope that's clear. Okay, thank you. Okay, so the other part of the question was compare string singly linked list and doubly linked list in terms of operations and memory use. Okay, compare singly linked list, it's basically a list. Okay, and doubly linked list, it's also basically a list, but in this guy we only have the arrow from A to B. In this guy, the doubly linked list, we have the arrows from A to B. So A links to B and B links back to A. Now in terms of operations and memory use, okay, I think that one we can discuss. Let us begin with the memory use. Which one do you think uses more memory between the singly linked list and doubly linked list? Which one do you think uses more memory? That's a question there. Okay, so that's very much true. So let us just discuss that. Keep the answers coming. Compare singly linked lists and doubly linked lists in terms of operations and memory use. Yes? Yes? Hello, do we have people in the meeting? Do we have people in the meeting? I think we discussed this previously. I think we discussed this previously. We are revising. So it doesn't have diagrams. So we want we want to discuss that verbally. Even more answers are welcome. Oh, please go ahead. Okay. Let me draw this so that okay, so that we answer that question. Let me just capture this. Let me just capture this. Okay. Okay, so let me just present this so that we answer that. Are you guys able to see? Are you guys able to see? Are you guys able to see? Okay, good. Okay, so I just hope it's clear. Let me just confirm. Is it clear there? Can give me a thumbs up. I hope it's clear. Hello guys. Kindly give me a thumbs up. Is it clear there? Okay, fine, it's clear. Please keep those thumbs up coming. We just want to ensure good. When you talk about the memory use, if you look at the singly linked list there, what we are just saying is every node has the part which keeps a value and a pointer. I hope you remember that. So in the singly linked list, the last part will be now. It will be closed like that. Okay, and you're going to have just 1 1 1 there. So you'd find that the space which is going to occupied by this, it will just be a node and a pointer. So you'd find that you don't have an extra arrow coming from there. So that space which is either at bottom or the top is not occupied. So this uses a small memory there. It is memory efficient. Now when you look at this, you have the top arrow and the bottom arrow. So this uses more memory because instead of having just this data and the pointer, you are going to have data, point and pointer. Okay, so this is 2 against 3 there. So if you count 1 2 3 4 5, then 1 2 3 4, your 5 just there, but 6 7 8 9 10. So for these 3 nodes, okay, and for these 3 nodes, 1 2 3, now there 1 2 3 4, you'd find that this is 10 times compared to that. And in terms of operation, basically this is linear, so this keeps on going. So 1 2 3, you can add that one, 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 and so on and so forth. So this becomes the order of n, and a doubly linked list becomes the order of n squared, because you go, that's 1, you come back, that's 1. So you're doing this twice, and so on and so forth, coupled with what we basically discussed previously. I hope that helps. Dan, does that help?
Yeah. Yes, very much.
Okay, good. Everyone else is okay? Is everyone else okay? Can you give me a thumbs up? Okay, good. The other question is, given a binary tree, explain how a perfect please pardon me, I'm reading words which are not there. So given a binary tree, explain how to perform an in order traversal, both recursively and iteratively. So given a binary tree, explain. So when they say given a binary tree, it's the same as use a diagram. So you have to give them a diagram. You come up with one. Okay. Give me a minute. Okay. Okay. Where? Okay. So when they say given a binary tree, you have to come up with it's a smart way of saying use a diagram. Okay. Then using that diagram that you are going to come up with, you explain how to perform an in-order traversal. Okay. Both recursively and iteratively. And we know recursively already is what we've been doing, and iteratively we will come to that. So recursively is the same thing that we do. Recursion is basically a method that refers to itself or keeps calling itself back to back. So recursively, okay, let me present that. Kindly give me a thumbs up. Can you see that? You know, the funny thing is, most of the times, it's kinda difficult if you miss the actual discussion, because there are questions that you may ask while the discussion is going on that you can't ask by watching a recorded session. So it's better to attend first, then you revisit. Okay, so recursive is the same thing that we've been doing since time immemorial. What we're just saying, visit the left subtree. Okay, so you have a subtree there. This is a tree on its own. I'm sure you can agree. Then visit the root. So you have to visit the root. Then visit the right tree. That is in order. So the left child first, the parent next, then the right child. That is basically what you're doing. And to make it even more interesting, you can put letters here, just at random, A, B, C, D, E, F, G. Then you put them there according to the way you're going. So you have that, you can't visit that, you have that, you can't write it, you have to write this. So if this is C, you put C here. Then you come to this B, you put B there. You come to D, then you go back, you put this guy there. If it is going to be A, you come to this, you put this one there, then this one, then that one, just to demonstrate how you are going there. Okay, so basically iteratively is basically the concept of a stack. Okay, so you use a stack by pushing all the left children first before until you don't have anything left. Then you pop those nodes one by one. The process just repeats itself on the right. So it doesn't mean you create another. Just this is fine. Then just explain what you are doing. So you process that, and you move. This is not the more. It's MOVE. So you move to the right. right children and repeat the process. What process? You push, okay, pushing all the right nodes until the stack remains now. Okay, I hope that's clear. Is that clear? Is that fine? Okay, good. The other question was proving this, and we have done these lots of times. We have done these lots of times. If they come, well and good. It is basically a bonus for us all. We have done these. I think we've been doing this since time immemorial. So prove that, then we just say, okay, we let some letter be equal to what is on the left. Okay, what they wanted was us to prove that log A base B is equals to log A base C over log B base C. So just focus on the left hand side to prove right. So you let some value, okay, some letter or variable be equal to what is on the left. Then you convert this log to exponentials. That's very important, and this is what we are saying. The base goes crosses the equal sign and lifts that x there. So b to the power x. The moment we do that, kindly give me a minute. I'm in the meeting there. We'll call you back. Okay, please pardon me for that. Okay, so our focus, wherever we are told to prove, just focus on your left. Make some value or variable equal to what is on the left. Then this base lifts that guy. Okay, so this here I just exchanged x for the log. So x comes this side, log comes this side. It doesn't really matter. So this goes and lifts this, which is that, and a remains. Okay, then at this point just introduce logs to both sides. So this will be log a. What you introduce this side, introduce that side. So log b to the power x. And we know that wherever we have an exponent in logs, just take this this x on the leftmost, okay, which is that guy. Now make look at what look at the way things are written. Okay, look at the way things are written. It's log a base b. So in that regard, what you want to prove is log a. Okay, so in this regard, you divide the log. You can basically introduce the bases right there. After that, okay, mama, that's pesa. So log, introduce the base just there. Introduce the base, this same base. Okay. Remember, just make that x the subject of the formula. That's very important, and that is one way of doing it. So the moment this x come here, divide anything else rather than x. So when you divide here, what you've divided here, you divide it even right there. So when you cancel this, you remain with x. So that is the x, log a, then log b to that base. But x, remember, your x is log a base b. Just remember that. That means wherever there is x, replace back that guy, and you have that solution. And that's what we say. That's how we prove that. Is that good? Is that good? All right. We'll be able to share the recording on the YouTube later in the evening. The other part was proving this. I think we've done this lots of times. You can use letters of your choice there. I decided to use C, A, and D. Okay, you can use L, M, N. Anything you can use. So we let C be equal to what is on the left, which is that. A is equals to that part, and D equals to this part. Okay. Then just always when you're having logarithms, convert these to exponentials. So b is the base, we'll lift c, which is this. The moment we have that, we have xy. B is the base, we'll lift a, which is that. The moment we've done that, we've remained with x. B will lift d. And the moment we've done that, we remain with a y. Mwakwisa mama. Oh, okay. Okay, that's quite important. When you do that, then just always work with the left hand side. Always. Okay, not almost always, but always work with the left hand side there. So that is the left hand side. Okay, you have b to the power c is equals to xy. But what is x? The goal is to make this x the subject of the formula and this y the subject of the formula. The x is b to the power a, so wherever there is x, there is b to the power a. But that's multiplication. Okay, you multiply there. Y is b to the power d. Y is b to the power d. Please go ahead. Hell no. The screen. You guys should be saying. I was busy explaining the concept. Where did we... were you hearing me? Were you hearing me? No. That's bad. Where did we leave you guys? Where did we leave you guys? Why did we leave one another? Where did we leave one another? So that we get back there. Please unmute yourselves. Hello. No. Okay. Right. Right. Okay. I think my screen should be back. Okay, so we have that. So let what is on the left hand side be equal to some variable, there be equal to some variable, and that be equal to some variable. Then change these logs to exponentials, and we know that the base lifts that guy. So when you lift that guy, you remain with xy, which is this. B will go and lift a. You can use letters of your choice, that's fine. B lift a, you have that, then x remains, then B lifts D, and this remains. And always work with the left hand side, and that is your left hand side. Okay, B to the power C is equals to a double equal sign. Where did I get that? Okay, yeah, it was an honest mistake. XY, then just replace these guys. Your x is B to the power A, which is that, but this is multiplication. B to the power D, that's your y. And when we are doing this, whenever we're multiplying, we add powers. So when we add powers, B and B will cancel, then we remain with C is equals to A plus D, which is that. But then bring back those guys. C is equals to log xyb, A is equals to log log xb, and D that. Remember always to replace this part. You have to say since. You can use since here, you can use but, you can use remember. Those key words or terms must always comes out. Then you say, okay, before equal sign we have a C, but C is that, so you replace back. A is basically that, you replace back. Then there is plus here, this plus is basically that, then D is that. That's how you show that part. I hope we are fine, we are okay. Are we good there? Right. Thank you. Please pardon me for that. Okay. 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 So analyze the best, worst, and average case time complexity of linear search and binary search. Okay, I think we have discussed this. Okay, analyze the best case scenario, worst case scenario, and average case scenario time complexities of linear search and binary search. And wherever we're talking about binary, we're talking about 2, and linear is basically in that. So good. So we have discussed, without wasting much time, a best case, worst case, and average case. Linear case, basically we are just go in line. So each movement we make, we are going to find the value there, even in the binary, because we have at least one. So we are going to find a node there. Okay. But the worst case in linear search, if we have a node here, 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 a node there, these nodes will keep going. Let's say this was node A, node B, node C, node D, node E, node F, and so on and so forth. The searching will just keep on going. If we want H, we'll start right from the beginning. We go in there, we go in there, we go in there, we go in there, we go in there. So we are going through or searching through any times. Okay, always remember to use the big O. So we are searching through n times. Okay, the best case is always 1 because that is the entrance. And then the worst case is basically n, and the average is n. Why? Even if you divide that line or that linear search in half, then you say, okay, since I have 1000 here, I have 1000 here, 1000 plus 1000 is basically 2000, and when you divide that by 2 divisions, it will still be 1000. So you keep moving from 1 to 2, 2 to 3, 3 to 4, 4 to 5. Even when finding the average, you are basically going to go through that n times. Before we come to binary, is that fine? Is that fine? Okay, good. Binary search, we are basically looking at at least 2, but always the first entrance is basically 1. So the likelihood of finding the node is always 1. That's the best case. Okay. We are using log n because this doesn't grow as much as linear search grow. Remember, you have a node here, for example, and a node there, for example, a node here and a node there, a node here and a node there. So if you have A here, B here, C here, A here, D here, K there. Okay, so the chances of finding D are very very high. So you can visit this, you don't find it, you can come back to this down, visit that. So you'd find that before you go any further, you also look at in the second line there. Once you look in the second line, chances might be there of finding what you are looking for. We are not just depending on a single line, we are depending on another guy. So if you have 2 lines, for example, of writing an exam, we are saying let's form 2 lines. You can go through this line, you can find a girl. You go through this line, the chances are there of finding a girl. So if before you progress further, you go to another line, the chances might be there. So that doesn't grow that much. Okay, the search grows logarithmically. Okay, does that help? Kindly give me a thumbs up. Okay, good. Right. Let's see. see. Okay, section C. I think we limited ourselves to a few questions. Question 3, question 4. Okay, so we answered question 3 and 4. Then there was also section D. Like, seriously? Hell no. This paper was very long. Let's see. Section C, 1, 2, 3, 4. But where did I get section? Oh, maybe it was D1. Hey, give me a break. No. Am I looking at the wrong sheet? Let me do this. Build a balanced tree. What did we have there? Design queue using 2-stack. Representing adjacent list. Okay, I'm looking at the wrong guy. Fibonacci. Three essential parts: structure, that. Okay, so we have done away with section B. Then section C, we do section C on Monday. I hope that's okay. Is that okay? We clean your video, upload it, and okay, thank you. I think see you on Monday. Yeah, see us all on Monday. Right, a good day for now. Let me just clean the video, I upload it and share the link with you guys.